important in especially in terms of experimental measurements and so on. Not directly, nobody can measure the partial molar property, but from change in volume and mixing, the partial molar properties, experimentalists seem to like to get that from the data, and which in turn throws some light on the nature of interaction between the various species in the mixture. So it's more of a theoretical insight it gives rather than on the nature of the mixture. So when we take a closer look at it, we can take let's say let's take a volume to be 0.3. That volume and enthalpy seems to be the most commonly studied from the point of view of changes due to mixing and partial molar properties. Now we have seen that the definition of the partial molar property, so we can always substitute the volume with any other extensive property that you may wish, and you get the corresponding partial molar property. So partial molar property requires that you have expressed the extensive property in terms of the temperature, pressure, and the mole numbers. That's the first thing you have to keep in mind. Each partial molar property of each of the components is simply the derivative of that with respect to the corresponding mole number. So it gives an indication of how the volume will change, volume or enthalpy or whatever, will change when you add a certain small amount of the substance. That's what it really represents. Right? The writer says delta V by delta Ni. For small changes in Ni, it will give approximately the value of the derivative. So how the volume changes, right, when a particular substance is added, that is a measure of the particular partial molar property. It's clearly very much dependent on the not only the temperature pressure but also the composition of the mixture. So it's defined for. Now the question is, how do I express it in terms of the mole fractions? Because we know that this actually is a function of the C-1 mole fraction. This is somewhat like the chemical potential, which also involves derivative of an extensive property with respect to the mole numbers. And we saw, for instance, we are going to express the chemical potential. We saw that one way of expressing it was and then corresponding expression for mu c, which I am not going to write down. You can see that all the quantities on the right hand side are all intensive or specific properties, or can be related to the actually the derivative. You notice, for instance, that P is simply minus dE by dV, and S T is dE by dx. Everything is expressed in terms of E and S and V. So given a fundamental equation, I can get this chemical potential. Now I can also write this as A plus PV is dA by dZ I, again for I equal to 1 to C minus 1, minus sum over you should be able to understand how this is possible. Because we saw that this is nothing but mu I star. This is mu J star. We saw how each one of the mu stars can be written in terms of any of the fundamental quantities. Only here, the derivative, which I have written explicitly, would be with respect to Tv and the other mole fractions. Here it is with respect to Sp. Now I come all the way, and then I can also now, like again here, P is minus dA by dV. A is of course the variable itself. P can be obtained from A. All the other B is a natural variable for A. Everything else can be obtained from A. That is another another way of writing it. So now, the last step in this, I can write this as G plus and then I can also write the mu C correspondingly in terms of G and its derivative and its natural weight. Now within all of those for the chemical potential, now can you tell me or can you write, let's say I equal to 1 to C minus 1, let me write. Is there the answer to the partial molar property with respect to volume or any extensive property? Which one of these set of expressions would you choose? By this inspection now without deriving, right, anything, because we have to really convert this, which is a function of Tp and N1 and N2 to Tp and Z1, and then go through the whole chain rule again. But I don't want to do that because implicitly I already done it. Now, among all these formulas that I've written for the chemical potential, which one would you pick to write the formula for the partial molar property? G, the one for G, because I know that this is nothing but GIPM, and so I can easily, I can also directly prove it, but I'm not going to do it. It's just another exercise in calculus. So I'm not going to write by simply inspection DIPM in terms of the temperature pressure in the mole fractions rather than the temperature pressure in the mole numbers as V plus dV by dZi minus sum over j equal to 1 to C minus 1 Zj dV by dZj. But I am now referring to, I'm sorry, yeah, this is expressed. So actually, this is how I will do this. So we know the specific volume can be expressed in terms of temperature, pressure, and mole fractions. And this is there, so there's actually a dependence on N also here, but I will ignore it. And dCPM would be D minus sum over A equal to 1 to C minus 1. And finally, we then get also that DIPM minus dCPM is actually equal to dV by dZi. Because here it is Tp and Zj not equal to I. We get the analog. The analog of this here is mu I star is equal to mu I minus mu C. So we get all those expressions. However, inferred you might wonder, but I'm making use of the fact now all these expressions for the chemical potential, the one involving G will actually correspond to the partial molar property of the Gibbs free energy. So I sort of got this indirectly by first working on E, which is much more complicated to do. If you look at the dependence on N in E, and you follow the whole procedure that we outlined using the chain rule and all that, you can see that all of these are dependent on N. S is after all capital S by N, which involves all the C mole numbers and so on. But if I come, I could have directly started with G of Tp and G here of Tp N1 and C. And I could have got this directly. That's what I have to do if I want to get this directly for any property, extensive property, partial property. That's what transformation I have to do. Here I did this. This is in fact more complicated because it involves the values S and B which also come into play. When you're working with G or any representation involved between the temperature and pressure, the procedure is actually easier because these two variables are not dependent on the mole numbers. But anyway, this formula you have to keep in mind. Although I don't expect you to remember it, it very much follows from the expressions for the chemical potential expressed in terms of the quantity G. Big story in that. If you really follow the whole set of advised to write this merely by inspection. So I don't want to go through the whole procedure again for B or S or G or H in terms of T, P and the mole numbers. So you take this as given. Now what is the advantage of this? Basically, naturally the partial molar property, as you can see, is a function of Z1, but by its definition it is directly dependent on an additional variable, because if you see that something is a function of temperature, pressure and mole numbers, well, the derivative of that with respect to Ni will also be a function of that. Is how it is introduced. The quantity is introduced through that. And so, however, there is a C plus 2 variables, but inherently partial molar property is like an intensive property. So it should be expressible in terms of the intensive and the specific variables alone. So this is also sometimes useful. Often the expressions you find in the standard textbooks express not the volume, the total volume in terms of the mole numbers, but rather the specific volume in terms of the temperature, pressure and mole fractions. So then these expressions will be directly useful. Even though obviously they are much more difficult to remember, because of all these terms coming together, this is clearly the easiest way to remember the partial molar property. Are there any questions on this? No, there is a whole set of equations called the Gibbs-Duhem equations, which you will find in the literature. I now show how to derive the Gibbs-Duhem equations corresponding to the partial molar property. So first, the earliest form of the Gibbs-Duhem equation comes from these relations. You recall, it's a crude way of deriving one of the many equations known as Gibbs-Duhem equations. You might wonder which one is the actual Gibbs-Duhem equations, right? In fact, other than the one that I'm going to write down, none of them were actually proposed by Gibbs. Probably they were derived by Duhem. So if you look at the Gibbs relation for E, it expresses E. This follows directly from the Euler's theorem for homogeneous functions, and recognizing that E is a homogeneous function of order 1 in each of its extensive variables. They are written here, right? So this then follows that this is Ts minus Pb, the sum over. We also have the general equation, which is this. Standard way to derive the Gibbs-Duhem equation is simply take the differential of this. Even though I don't approve of this procedure because it doesn't give any insight into the actual significance of the Gibbs-Duhem equation. If I take the differential of this, I have to write this as dds plus SdE. So it gives the correct answer very quickly. Minus PdV minus PdV, right? Plus sum over j equal to 1 to C. Nj plus sum over j equal to 1 to C Nj. Very easy to write down. Just take the product rule for differentials, and then we get all of this. Now, if I introduce this, if I substitute for dE from here, you can clearly see that this will get cancelled, this will get cancelled, and also this will get cancelled. I substitute for dE from this, put dds minus pdv plus sum over j equal to 1 to C mu a dnj. I substitute that here, then I can cancel these terms, and all I am left with is this is equal to 0. This is probably the first equation which was derived, which is now referred to as the Gibbs-Duhem equation. Certainly it's entirely due to Gibbs. He has it in his book, in his paper, first paper. So this is one version, but then there are so many other equations also called as Gibbs-Duhem equation. Basically, at any condition of homogeneity is an expression expression, Gibbs-Duhem equation essentially is that, nothing more than that. So there are various expressions. This is also expression of homogeneity. There is a valid only for homogeneous states. Somehow the one involving the temperature, pressure and chemical potential is what is given special prominence and referred to as a Gibbs-Duhem equation. So now when it comes to partial molar properties, there are several types of Gibbs-Duhem equation you will find, and I will derive 3 of them. It will probably exhaust all possible forms of the Gibbs-Duhem equations for partial molar properties. And so I will simply erase this. So the first 2 that I am going to write down involve the mole numbers. The last one, probably the most important one, involves the mole fractions. So let me just stick to volume, although it can be done with any partial molar property. So first I recognize that the volume can be written like this. We have already seen this in the expression of homogeneity, and because the temperature and pressure are intensive variables, these are the only extensive variables. This is the whole purpose of introducing the partial molar quantity. But we have a compact expression like this, much like how G was expressed in terms of the chemical potential. So now the whole trick is simply differentiated with respect to an arbitrary mole number. You can remember that step, you can get the Gibbs-Duhem equation. So let me now differentiate this, because after all that is the partial molar property. So it requires differentiating the partial molar property also with respect to Ni. That is what we need to the so-called Gibbs-Duhem equation. So dP by dNi. So I am now picking a particular Ni. I am going to differentiate the left hand side as well as the right hand side. Left hand side will give me the partial molar property of the ith component, right? So dP, this is after all equal to VIPM. Nothing new in that. But what we get when we differentiate this, so I can take the derivative into the sum and then differentiate term by term. So I'll first write the easier one. Right? So I'm taking the derivative because the derivative of the sum is the sum of the derivatives. Now when I go in, I see that each term is a product of 2 terms. So I have to differentiate each of the 2-term factors in the product. So I have done once, I have differentiated dVj by dNi. First, again, sum of again you want to see Vj Pm times the derivative of Nj with respect to Ni. That is clearly delta Ij. You have seen it repeated. Now this is sum of again you want to see Nj dVj Pm by dNi plus Vj Pm delta Ij is the sum over j to all components, right? So when j equal to I alone, delta Ij is 1. For all other cases, delta Ij is 0. So all the terms in that sum will be 0 except when j is equal to I, the particular I that I have chosen. So this will simply be VIPM and delta II, which is 1. So clearly then VIPM is getting cancelled, and so I get the Gibbs-Duhem equation. So implies j equal to 1 to c Nj dVj Pm by dNi equal to 0 for I equal to 1 to c. So there will be c Gibbs-Duhem equation. We see the significance of this later. They are not very necessary in your calculation, but they sort of give a test on your calculation sometimes. So this is one form of the Gibbs-Duhem equation. They basically involve the derivative of the partial polar property with respect to the mole number. This is one form. Now, if you look at the other form, can be very easily obtained. If you notice that djpm, which is what I have here, is dv by dnj. K not equal to J. That's by definition. Simply written for jth component. Now, if I take the derivative of that with respect to ni, which I can do, right? So, d by dni would be d by dni of that. Now, giving all temperature, pressure, and all variables other than I fixed, right? So now you can see that I can interchange the order of differentiation, and so this can be written as d by dnj of dv by dni, now giving dv k not equal to I. Okay. So that is what I have. So this is nothing but dipm, right? So this is d by dnj of dipm. So I now get the other form of the Gibbs-Duhem equation, which is j equal to 1 to c. So what follows trivially from this, dvipm by dnj. Yeah, is equal to 0. You have to be very careful how this. There are two indices I and j. One of them is the summation index. The other one, I, is corresponds to one component. So you will actually write this for each one of the C components. So you have to be very clear not to mix up the indices. I equal to. So be clear which is j and which is I. This is j here and this is I. So here j appears twice. Here the also j appears twice actually, but it appears here in the derivative in j here. There it appears on the numerator. So best not to remember it, because you might wonder how whether it's j or I or what it is. But clearly this starting point is very clear. All you have to remember is differentiate it with respect to ni, and you will get the Gibbs-Duhem equation. So these are the two forms in terms of the mole numbers. Now in terms of the mole fraction, there is only one form, and so it's important to be even more careful with that. The idea is the same. Instead of since there I have the specific variables come in, what I will do is simply divide v by n. So my starting point is the same, my requirement is different. So I start from v. Now I divide both by the total number of moles. So clearly then this becomes an expression for the specific volume. This will apply to any property. You have the enthalpy, you will get the specific enthalpy in terms of the mole fractions. Here now I have to be careful, because B, the one I want is B as a function of Tp z1 up to zc minus 1. So that here I will now differentiate with respect to zi, but I have only c minus 1 mole fraction. But I have to be very careful. The c mole fraction is not independent of the other c minus 1. So I want to write this as, so this is the first step, very easy to see, because my purpose is in terms of derivatives of v with respect to zi. That's what I want now, because I want to give you v in terms of the mole fraction. So I have to switch to the specific variable formalism. So now I write this as a equal to 1 to c minus 1. This will be a little bit trickier. So the c term would involve set C. Right? So that set C, I'm going to write it as 1 minus sum over j equal to 1 to c minus 1. Set j times bc comma pm. So I have now got everything in place. C minus 1 mole fractions, which is all I want. I don't want the C mole fraction hanging out there. It's very convenient to write it in this way. Whenever you're going to do an operation that has to explicitly recognize that only C minus 1 of them are independent, then you have to be careful the way you write it. This is the problem with the mole fraction formalism. So now I am going to differentiate with respect to Zi, the whole equation. So now I pick a particular mole fraction. It can be any one, the C minus 1 only. Right? So I equal to 1 to C minus 1. Procedure is very similar. Differentiation will be a little bit more tricky because of the additional terms that have to be rewritten. Here all terms have the same footing because all whole numbers have the same footing. Here set C has to be changed, right, to recognize that it is not independent of the other. So dp by dt set I is, procedure is the same here, but here sum is over C minus 1. So first I write the easier term. Again, taking the derivative into the sum, now differentiate the product term by term, right? So I get this sum plus Pj Pm dzj by dzi, again to be delta ij. So I am restricting myself only C minus 1. This is also C minus 1 delta ij. Here 1, this is BC Pm, so that would involve EBC Pm by dzi or let me write it let me write it like that. So I'm just taking the BCPM inside, so it would be easier to let me write it like this. So first let me consider this as two terms, this versus this, right? So first I will differentiate this with respect to Zi. I don't want to complicate. So dBc Pm by dzi times, now I won't differentiate this using the product rule. This is 1 minus j equal to 1 to c minus zj. I will simply write it as zc for convenience. Now I can write it as no problem because I am just replacing that quantity by zc, which I know is zc. If you want, I can put it as 1 minus sum over. To simplify my writing, I am putting this. Here, BCPM, now I have to differentiate this. Right? So clearly, 1, when you differentiate 1, nothing is 0. Now minus sum over j equal to 1 to c minus 1, right? I go inside and differentiate with respect to zi, again I get delta ij. Right? So what is the sum? J equal to 1 to c minus 1 delta ij. 1. So there is nothing here. Of course, this BCPM multiplying it, but so this is now I can rewrite this whole thing. So dB by dzi is equal to dB by dzi is equal to sum over j equal to 1 to c minus 1 zj plus this is BIPM delta ij sum is there. So this is BI comma PM plus ZC times DBC PM by DZI Now you see why the mole fraction formalism is always a tricky one. So many terms, additional terms are there. And then plus PCPM times is minus 1. So it will be minus PCPM. So now if you see here, I've already written that in anticipation. dB by dzi is VI PM minus PCPM. This is analog of mu I minus mu c to mu I star. So these two terms together will cancel with this. Now I have Zj j equal to 1 to c minus 1 Zj dB j PM by dzi. I have Zc dB c PM. So now I can put them together. Rather than writing as 1 minus sum over j equal to 1 to c minus 1 Zj, I can now write this as sum over j equal to 1 to c Zj dB j PM by dzi is equal to 0. So this is the third form of the Gibbs-Duhem equation. Importantly, this is I equal to 1 to c minus 1 1. So there will be one less equation. So we are dealing with one less variable. So you have to really see the application of this, then it will become clear. The derivation I don't really bother, but you see that it's well within the reach of what we have covered so far. But you have to be really careful when you are in the mole fraction formalism. Here the other form, because dBj PM by dzi is not equal to dBi PM by dzj, you can easily verify that. It's not going to be possible to do that, and you can verify why that is. So if you don't get any other form, you have to see why that is not the case. You may wonder, it's the same thing interchanging of derivatives, should that not work here? Don't work here. This is the only form. So here you have to be very careful. The indices are here. You cannot interchange the I and j here and get another form of the Gibbs-Duhem. These are the three basic forms of the Gibbs-Duhem equation. Right? We'll see its utility later in the next class. But before that, I probably would prefer to end the class by showing you some pictures so that you have got relief of this tedium of going through all the derivations. It's only the final equations that are important, not the derivations. And it's a bit too involved, and especially judging from performance in the first place, I probably would not venture asking any of these derivations in great detail. That doesn't mean there won't be any derivation at all, but one would have to be a bit realistic, I think. But the final equations are very important. You don't have to remember them, but you have to know how to apply them and where they are useful. That may be clear. So these are some pictures from the standard textbooks. Some pictures of the you can switch off the lights. These give various forms. How these we have to read out the x and y axis. Which one? Why do you have to do it?
Dust equip.
Make me first take one of the other.
No, chet pe.
Keep it there. Yeah. We still have about 10 minutes left from the promised extended class.
Please clear.
Certainly will be there. So what you can see here, this is delta V mix. This is actually a delta bar that we should really introduce. Right? What you see on the left side is the delta V mix, and the curve you see here below is methyl formate versus methanol, and the other one is methyl formate versus ethanol plus methanol, mixture of methyl phenol versus methyl formate and ethanol, the one on top. So you can see delta V mix. This is because it's a change in volume on mixing that we talked about. So it's basically what is plotted is delta bar actually by other notation V mix minus, here there are only two components, J equal to 1 to 2, right? Xj or Zj Bj. So we have the ethanol or methanol and methyl formate separately. We add them. This will give an indication of whether the volume is going to increase or, because volume is not conserved, going to increase or decrease. You can clearly see that with respect to ethanol, right, which is also an alcohol, it is one away from methanol, the higher alcohol, the volume actually with methyl formate is increasing, right? Whereas with methanol, the volume will decrease, volume of mixture will be less than the individual pure compounds. So this gives some idea of how the nature of interaction between the components. Now if you look at very similar, this is the enthalpy of mixing. An enthalpy of mixing is benzene, right? So what you have is C6H6 and C6F5, so the fluoro halogens, hydrocarbons. So C6H6 plus C6F5, Y, the Y is H, Cl and so on. So you can see that Y is equal to H, which is C6F5H, right? Some hydrofluorocarbon maybe. So for that alone, you see a volume, enthalpy increase. So this is now an enthalpy change, which is positive on mixing. That means heat would be released when you add make up the mixture, right? So H is all the others. Of course, the F also has a belief. It's also a function of composition. It's not going to be always positive necessarily. So in some cases, you can see that F, that is C6F6, enthalpy is increasing initially of the mixture, of the mixing, enthalpy of mixing is positive, and later on it becomes negative. So the whole question is, what the experimentalists end up doing is how to get the partial molar volume or the partial molar enthalpy from these figures. We will see a geometric interpretation of those equations in the next class. And then I have some other pictures to show. There you will see the effect of the Gibbs-Duhem equation coming. This one is, I don't know, this is certainly from Sandler. This one I will verify which book I just happen to have it. And this one, here, what the point made here is, let's look at the top figure alone. And this is a carbon tetrachloride benzene mixture. Right? So carbon tetrachloride is 2 and benzene is termed as 1. So this is an mole fraction of carbon tetrachloride. So pure benzene, this is pure carbon tetrachloride. The point he is making here is that he has also got from the mixture volume, which again goes through a maximum here, mixture volume, and that is different. That is the change in volume on mixing the earlier figure. This is the actual volume of the mixture itself. Because that seems to go through a maximum. But you see here, the partial molar volume of CCl4, this is a binary mixture, it is decreasing with composition, and correspondingly, the partial molar volume of benzene is actually increasing. So this he points out for a binary mixture, this is bound to happen. This shows that the Gibbs-Duhem equations are at least qualitatively satisfied. So if you look at the Gibbs-Duhem equations for the binary mixture, what I have written here, this would be Z1, right? I have only one Gibbs-Duhem equation, so I equal to 1. So that would be Z1 dV1 Pm by dZ1 plus Z2 J runs from 1 to 2 dV2 Pm by dZ1 is equal to 0. So you can clearly see if I take it over to the other side, Z1 and Z2 are positive, so there is a negative sign here. So if dV1 Pm by dZ1 is wherever it is positive, this will be negative, and wherever it is negative, this will be positive. So here you see one is benzene. So because the partial molar volume is increasing with composition, right? Maybe they have here X2 plot, it might not quite good, but I can take Z2 as the variable. So this will work. I can take it, maybe this is not, the notation doesn't match, but you can clearly see that if one of the partial molar volume is increasing with composition, then in that composition rate, the other one would be decreasing because of the negative relation between the derivative of the partial molar property with respect to the mole fraction. This is true only for binary mixture, but ternary mixture there will be another term, so we don't know how the terms are going to balance out. Right? So now the third figure is somewhat unusual, and that one is showing even a negative value for the partial molar quantity. This is sodium chloride solution. Right? You can see at a higher temperature, the partial molar volume itself is becoming negative, somewhat unusual. The explanation that the authors have given is that this indicates, so what happens is that when partial molar volume is negative means what? You have to look at this formula, dV by dNi. So when I add sodium chloride, this is with respect to sodium chloride, right? Partial molar volume of sodium chloride. So that is the rate of change of volume of the mixture with the addition of sodium chloride. So what happens is, saying instead of volume will actually shrink when you add sodium chloride, and the reason given is that the interaction between the sodium chloride and water is much more with the attractive force than the interaction between the water molecules themselves. So when you add the sodium chloride, the mixture volume actually decreases. So even if you are not following the argument, clearly the point is that from the knowledge of the partial molar volume qualitatively, to get an idea of the nature of interactions at the molecular level between the constituents. That's one of the reasons probably people are interested in the partial molar volume. The last one, this is a somewhat complicated diagram, I won't spend too much time, but you can go through Sandler, the section on partial molar volume and enthalpy. This is a very somewhat involved figure because it also involves a phase transition. But this is a very famous system. Sulfuric acid versus water. What you have here is the enthalpy of the mixture. That is the actual enthalpy, not the change in enthalpy. Enthalpy of the mixture versus the weight percentage of sulfuric acid. The only point that Sandler makes that is relevant here, so whatever series of problems, and we look at some of the problems in the next stream. What he points out here is that there is always a question, a famous question, whether when you want to mix sulfuric acid and water, right, whether you want to add water to sulfuric acid or sulfuric acid to water. So Sandler points out correctly that the answer to that is in the figure. Because if you see, this is water, this is pure water, and this represents how the enthalpy is actually changing. Right? So this is going to release heat because the enthalpy is decreasing. What I said earlier probably was not correct. This is going to, the enthalpy is decreasing of the mixture, means that enthalpy has to go somewhere, it is released in the form of heat. That's what would happen when you mix And it happens in both cases. Whether you start from sulfuric acid, if you start from sulfuric acid, water also enters, the heat is released in both cases. But what he points out, if you see here, the slope is much less sharper than here. So even with a slight addition of sulfuric acid to water, to water to sulfuric acid, because this will be pure sulfuric acid, there will be a significant decrease in the enthalpy, a significant increase in the heat evolved. So he points out that the answer, because of the magnitude of the slope here is much smaller than this, it is wiser to add sulfuric acid to water rather than add water to sulfuric acid. Now we see more clearly the quantitative aspects of these features of the partial molar properties in the next week. Right? So are there any questions? If no question, then we are done for today. We meet again on